until now, okay, we learned the European option. This is European option. And then how about the American option? In case of American option, okay, European option means we can exercise option only at the last period over here, at the last period. But American option, for American option, we can exercise the American option anytime from right now to the maturity. Okay, I think this is maybe better. Okay, can you see the screen well? Is it okay? If the font is too small, please let me know. So let me use American option and then American option. Let me type text. Now American option. For American option, I will use a method called Longstaff Schwartz. This paper, Longstaff Schwartz. Longstaff Schwartz. Longstaff Schwartz, 2001, the review of financial paper, valuing American option by simulation, a simple least square approach. Okay, this is very famous paper. Okay, and then we will learn this technique, this famous technique. Okay, okay, this one. Okay, we will learn method described in this paper, very famous one. Okay, so, well, this one is slightly more complicated. In order to learn this one, we have to learn first about the polyfit function. Okay, so we need to learn polyfit function first. Okay, so basically polynomial function. How to find polynomial function that fits, okay, the data. So polyfit. So numpy so numpy polyfit function. NumPy polyfit function. So yes, there are manual over here. And then there are, of course, examples here. Well, yeah. And then I'll put the link over here. Okay. So where do we start? Let's start a very simple one. Suppose X. Okay. We have data. Suppose X equal 0 and 1. And then Y. When X is 0, suppose Y is 0. When X is 1, let's say Y is also 1. So we have a 2 point, 0, 0, and 1, 1. Then we want to find a polynomial function that exactly fits these 2 points. And that is obvious, right? That is a 45-degree line, X equal Y. Okay, so it is just first order. So let's say Z. Let's find a polynomial function. So NP polyfit. And then we can put data. And then we know the answer. So it is first order, X equal Y. Okay, so this should be the answer. Then let's print G. Right, so this is 0. So basically Y equal X. This is a constant term, right? So this is Y is equal. What if this is 2? When X equals 0, Y is 1. X is 0, Y is 0. And X is 1, Y equal 2. Then we have Y equal 2X. So let me try. Right, so we have 2, this is 0. What if we just add 1? Okay, in this case, obviously, the correct function is y equal 2x plus 1, right? So, yes, y equal 2x plus 1, constant term. And do you see what is the pattern? Yeah, so we are looking for polynomial fit function. What if we have 3 points? 1, 0, when y minus 1, let's say when x is 0, it is 0. When x is 1, let's say it is 1. When x was minus 1, let's say it is plus 1. Okay, then the polynomial function in this case, it is right. It doesn't fit very well because we need a convex function y equal x 제곱 x square, right? 0, 0, 1, 1, minus 1, still 1. So it is y equal x square. So let's try now. We need second order. So exactly we have this is 0, this is 0. So y equal x square. Okay. If we change it into 2, then it is y equal 2x square. Right? Exactly. Y equal 2x square. If we add 10 over here, okay, then y equal 2x square plus 10. Right? 2x square plus 1. Right? And then of course we can make it plus 2. If we do minus 2, then y equal x square plus x plus 10. It should be. Okay, 이게 2. So x square plus 2x plus 10. Right? Even if we add into third order, well, it doesn't fit very well now because we have 4 unknowns and then, right, we have only 3 data points. So up to 2, it is fine. Okay. Of course, we can make it more general. Now, let me add any number. Now, from now on, I don't know what is going on, but then, well, it will do its best to find the second order function that fits those points very well. Okay, it does its best. If we include up to fifth order, yes, we have something like this. And then let's say P equals, and P poly 1D, 2D, 1D, 1D, poly 1D. Okay. And then Z, import this Z function. And then let's calculate P2, P3. When P is 3, it has this one. Okay, so let me go back to the previous one. A very simple one. 12, 12. So this one is, as we know, y equal 2x squared plus 10. Okay, y equal 2x squared plus 10. Okay, and then we need up to second order. If you run it, then, well, it is 2x squared plus 10. If we add 3, then 3 squared, 9. 9 multiplied by 2 is 18 plus 10, 28, right? It is almost 28. Okay, so when P equal, let's say 30, it should be very big number. Okay, so this is a polynomial. This is a way to find a polynomial. Any question? Okay, we need this polynomial fit to execute, okay, to learn the Longstaff Schwartz method, least square approach. Okay, now let me delete, not delete, let's move this over here. Let's move on. One more. Okay. Any question up to this point? Next, about random number generation. In the previous one, we generated only one random number. In this case, we have to generate a lot of random numbers simultaneously. So let me say temp np random standard normal and say 2 3. Okay, now it works. Next, and then print temp. Okay, so we now can generate random matrix, random matrix where dimension is 2 by 3. So 2 row and 3 column. Okay. If we make it 20, then of course we will have 20. Yeah. So 60 random number like this. Yeah. Oh, not 21. So if we make 1, 3, then it is a vector. Let's say 4. Okay. This one. And then we have another interesting function for the cumulative sum. So let's say print np cumulative sum of temp and then x is equal 0. Okay. Let me put a gap. Okay. So here, x is 1, we are adding one cumulative add, this one by column. So, no, by row. So first line is exactly the same. And about second line, now this one is now this one plus this one. So this one is minus 1.45, which is approximately minus 0.99 plus minus 0.46. This one is minus 1, so which is summation of this one and this one, right? So you know the pattern. So basically cumulative sum over the each row. So the third row, this one is of course summation of this one plus this one, which means that this one is the summation of this one and this one and this one. This one 0.3 is the summation of this one, and this one. Okay. So by x is making x equal 0, we are adding this way, cumulative sum. Okay. Of course, we can make cumulative x is 1. Sorry. Then in this case, we are now adding in the column way. Okay. So now we are adding this way, So this one is, so this line is the same to this line, right? And then this line, this one, is the summation of these two. Okay. If you can see it, they are look similar, right? So column is cumsum x is 1 like this. Okay, so far so good. So I think we are ready. Now in American option, because in American option, the path is important. In the European option, only the terminal point important. But in American option, the path to terminal value is also important. Because during the path, through the path, there is a chance that the option is exercised because it is American option. So it means we have to not only the single point terminal one, we have to generate the path of the stock price. Okay, that's why we need to generate matrix of random number, and then we need a cumulative sum, because stock price at time t is the cumulative sum of the previous shocks, stock returns, right? So let me do it. So let me start. Okay, so we are basically using Longstaff Schwartz algorithm. Okay, I mentioned the paper. So let me import math, and then let me start from the beginning, and then import numpy SNP. Just a moment. Okay, numpy SNP. Okay, and then let's give seed of the random number. NP random seed any number. And then next step is like input specification. Okay, input specification, inputs. Okay, they are basically same to the previous one. Let me reuse it. Do I have inputs? Okay. Let me reuse input over here. Okay. Now, well, because initial point matters, so let's make this one S0. And then V, let's call it sigma, in order to distinguish from the previous one. So risk-free rate, mu, and then sigma dividend. This is dividend, right? Let's change the name, dividend T. Let's make it simple, just 1 year. K, we have everything. Okay, I think we have everything. So input, they are the inputs. Risk-free rate, dividend yield per year, expected return, and then exercise price, and then time to maturity. Okay. Now we are generating series of random numbers first. Okay, now series of random numbers. Oh, so first. Okay. Okay, let me specify simulation parameters over here. So number of simulation, number of simulation is 10 to the power of 3. Actually, 200 to make quick. And M, M equal, let's say this is the number of simulation. And this is a time step. So how many time steps we have? Let's make it 10. Time step. So it means dt. dt equal t over m. Length of time step. Okay. So let's say 12. So it is 1 year. So so t time to maturity is 1 year. So m is 12. So basically here time step is 1 month. So I simulate the stock price for series of months for the next 12 years. Okay. And then let's discount factor. Discount factor is of course NP exponential of minus R dt. This is the discount factor. Okay. Discount factor. NP. It's NP. Let me use math. Okay. Okay. So far so good. Now first, let me simulate stock price is first random number. Random number. So NP random standard normal. And then we have M plus 1. And then I, number of simulation. Okay. So it looks like this one. MP shape. Oh, I don't know why tuple is not callable. Yeah, 13 by 1. It is 13 by 8. 8. Why it is 8? I. Number of simulation 100. Okay, 100. Now it is fine. So here, yeah, 13. Okay. Okay. Here I think it is so. Okay. And then because it's only random number, so then I have to add time step, multiply time step over here. Multiply time step over here. So I multiply time step dt, but I have to do square root of dt. Actually, 네. Okay. Square root of nt. Okay. And then I multiply sigma, scale up by sigma. Okay. And then I have to add what? I have to add the drift term. So basically I'm doing this operation over here. I'm doing operation over here. Where is it? Yeah, basically this one. Okay, I am doing this operation. So here I have to add mu multiplied by dt. But of course, not only mu, I have to subtract minus sigma square divided by 2. Okay. So I'm basically through this way, I'm generating series of returns. Okay. So let me move this one. Okay, this is a return series. I'm basically generating series of return drift term, and the sigma, let's put square root this one over here. sigma square root, and then this one. I'm basically generating return series plus, okay, let me change the line, plus plus. Well, this is always, sometimes it works, sometimes it doesn't. Okay. Yes, here, let me just use one line. Oops, okay, so this is error. Now it should work, plus unexpected indent. Well, but this one doesn't look so cool. Anything? Okay, okay, this one fine. Okay, and then for stock price, then I have to of course exponential of the stock price, stock returns, return series, return series. But I have to do cumulative sum of the sum because I have to keep add, right? In the previous loop, I have to keep add. I have to keep add stock prices. Multiply stock return. Basically, of course, in exponential term, it is add at the power term, but I have to keep multiplying returns to reach the final one. So in the exponential one, in the exponential, multiplication is sum, so as MP cumsum of this one. Okay. But of course, the axis should be 0. EX. And then I have to multiply S0 from initial one. Right, this one is so pain. Okay. SX0 E cumsum returns. Actually, this one over here. Only size 1 array can be converted to Python scalar. Strange. Okay. So far, it is fine. And I have to cumulate it. Why? Cumulative with this one return series x is by x is 0. I think it should work. Only size one array can be converted to Python scalar. I'm not.
교수님, 그거 numpy 라이브러리가 다른 수학 함수랑 호환 안 될 때 뜨는 에러 문구입니다.
Because there is something I don't know how to correct this one. Then, okay, you are right. I have to use numpy. Okay, right. Because input is numpy, so well, instead of mass exponential, I have to use numpy exponential. You are absolutely correct. So basically, I'm generating a series of stock price. Print the stock price. Well, so yeah, it is a bit big, right? So here 13 step, 13 row. So in the row way, in the column A, it is one stock simulation. And then here, yeah. So this way is the one path of simulation. And this way is the number of simulation, right? So, good. I think this is the enough for today, and then let me continue from the next class.